Okay, good evening everybody. Let's start today's class. It's going to be on one of the most important theorems of electrical science known as Thevenin's theorem. Let's see what's the application and what is the genesis of formulating this theorem. In our homes also, say for example, you could have a complex system which is providing the power, right? It could be the commercial supply which is coming in conjunction with the say generator set, or you could have a backup UPS supply and things like that. So this is the case in most of the electronic circuits. Okay, there will be a system which is giving the power, and then you have various loads connected to it. Now you see these load, generally the input side which is supplying the power, there are no variables. Okay, more or less they remain constant and with time, whereas the loads which are connected across, they keep changing like depending on the consumer requirement. So every time if we have to analyze this circuit, this complex source, along with the complex source, you will have to do the mesh analysis, node analysis, and try to compute how the circuit is functioning. So Thevenin proposed that instead of that, if we somehow represent the entire fixed part of the circuit with a single source and a single resistance in series, then it will become only the variable which is the load can be separated from that circuit, and then you somehow make a small simple circuit with all the fixed elements lumped in, with being represented by a single equivalent voltage and an equivalent series resistance. Okay, so that is how this idea originated. Okay, so so let's see how it is done. So what is Thevenin's theorem? He said that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH, that is VTH stands for VThevenin, in series with a resistor RTH. RTH stands for resistance Thevenin. Okay, where VTH is the open circuit voltage at the terminals. That means what is VTH? When we don't connect a load to that the complex network of sources, then whatever is the voltage available across, so that means RL we are making it in infinity. Okay, so whatever is the voltage available, that will be known as VTH, and RTH is the input or equivalent resistance at the terminals when the independent sources are turned off. That is, when we are looking from the load side into the circuit, we remove all the sources, and then whatever resistance we see in seeing into the circuit, that is known as RTH. Okay, so I'll elaborate these things further in the next few slides. Okay, so what does the Thevenin theorem do? It provides a technique by which the entire fixed part of the circuit is replaced by a simple equivalent voltage source in series with an impedance. Okay. So that is the beauty of the Thevenin's theorem. It makes an complex circuits source a fixed part of the circuits in which there is no change. There is no change means the currents in that will change, the voltages within that circuit elements might change, but the elements per se, they don't change. Okay, there could be say, 2 or 3 sources, resistances. Those values of those resistances and those current sources, they will not change. But inside that, the currents and voltages might change across each element. Okay, that is not our botheration, because we are going to now think of the entire thing as a single voltage source in series with a resistance. Okay, so the important thing which we should not miss out here is, it clearly says a linear two-terminal circuit. Okay, that means the circuit has to be a linear circuit. And what is a linear circuit? A linear circuit is one whose output is linearly related or directly proportional to its input. Okay, that means the relation between the output and the input has to be linear. That is, it could be V is equal to I, or V is equal to L di by dt, or integral Vc. So those kind of things. It cannot be I is equal to V square. Okay, that means it's not linear. So the moment you introduce, so as long as you have R, L, C transformers in the circuits, it continues to behave in a linear function. the moment you have BJTs or MOSFETs or diodes in the circuits, then non-linearity sets in. Okay, they are not known as linears. Because that equation, if you see the current equation of a MOSFET is VGS minus VTH the whole square. So that kind of terms are there in the equations, right? So they are no more linear, and there we cannot apply the Thevenin's theorem. So this is only for basic electrical circuits, okay, with these basic elements, RLC and transformer. Okay, obviously there will be voltage sources and current sources also here. Okay, so that is now let's consider two networks. There is network 1 and there is network 2, which are coupled. So we are assuming there's only resistors, independent voltage and current sources in these two networks. So what we do is we remove that network 2 and try to find out what is the voltage between A and B. Okay, so that voltage it will be known as the open circuit voltage, or it will be known as the Thevenin voltage. Okay, so this network 1 could be complicated in structure, and there could be 100 meshes, 200 resistors, 10 voltage sources, 20 current sources, whatever the case may be. But ultimately this will be represented as a single voltage source. Okay, so that is where the importance of Thevenin theorem lies. So now we are going to now place a voltmeter across A and B and read the voltage. That is known as the open circuit voltage, which is known as the Thevenin. Now it says no matter how complicated network 1 is, we read one voltage. It is either positive at A with respect to B or negative at A, and we call this VOC, that is open circuit. It's also known as VThevenin or VTH. Okay, that is the second thing is, now once having computed VTH, we need to compute the RTH. Okay, that is the resistance we are seeing from right to left into the network. So what is the resistance which the network offers? Okay, so we need to deactivate all the sources and try to find out the resistance as seen through terminal A and B. Okay, so how to deactivate the sources? So the deactivation is by removing the source and replacing it with a short circuit in case of an voltage source, and in case of a current source we remove the current source and there will be open circuit there. So this is how we are going to deactivate the sources. Okay, voltage source we are going to short it, and current source we are going to open it and replace it with an open circuit. So now let's take an example so that things will become more clear. So here this is the circuit which is given here. We need to find out the net resistance as seen from A and B. So there are several voltage sources, and we need to remove those voltage sources and current source. So let's see how to do that. So if you see here, this current source is replaced, and you have an open circuit out here. This voltage source is short circuited out here. This voltage V2 is also short circuit, so you have an R2 directly coming. R3 you have I1 short circuited here. So this is the remaining circuit. So R1 parallel to R2, then you have one R3 series and then R4 parallel. Okay, so this becomes then you calculate the net resistance between A and B. That is R4 in parallel to R3, which in turn is in series to parallel of R1 and R2. Okay, so that is how we compute. So now suppose R1, R2 and R4 is 20 ohm and R3 is 10 ohm. What is the voltmeter going to read here? Anybody can just make a guess? R1, R2 is 20 ohm. Excuse me. So this becomes a 20 parallel 10, and then R3 it's in series, so R3 is 10, so again it would go up to 20, and then again R4 is 20, so 20 is parallel, so the net reading will be 10. So if you put a ohm meter out here, it will read as 10 ohms. Okay, so that is why. So that we get 10 ohms, and so then you need to find out VTH also. That is while along with these sources, what is the voltage which is going to be here, that need to be found out, and that will be represented as VTH. Okay. So and then once after finding VTHN, the entire network one can be replaced by a single source and a single resistance. Okay, so this becomes pretty simple to solve. So in many cases, even the if even the network 2 is fixed and you find we can again make an equivalent of it and put an Thevenin voltage and resistance, and we can do even this. Okay, so even this is possible. There are two networks independently. You replace them with the Thevenin and Thevenin voltage source and a Thevenin resistance in series. For the network 2, you do the same thing and then interconnect them. Okay, so this kind of arrangement is also perfectly fine. We can do this also. Okay, so what are the steps involved in this, right? Okay, so if the terminals A and B are open circuited, and that is to find the Thevenin equivalent voltage, whatever is the load which is there, we should remove the load and try to find out. Okay, so RL should not be included into the circuit while computing VTH. Okay, so that is the rule you got to remember. So if you are going to do by including RL also, then the answer is wrong. So you need to remove the load and then try to find out what is the voltage across AB, and that is open circuit voltage or the Thevenin voltage. Now to find out the Thevenin equivalent resistance, there could be two cases. Okay, in case one, when the network has no dependent sources, okay, all are independent sources. In that case, it is straightforward and simple. Turn off all the independent sources. When I say turn off, replace all the voltage sources by a short circuit and current sources by an open circuit, and then find out VTH. Okay, and then find out the total resistance across the terminals A and B. But in case the network has a dependent source, here this situation is slightly different and it is slightly complex. In this case, again we turn off all the independent sources whereas the dependent sources will continue to remain there in the circuit. Okay, we are not going to turn off those dependent sources. They will remain there. Okay, and we are going to apply a voltage source across the output terminal and determine the resulting current I0, and then to compute RTH we write V0 by I0. Okay, so is this aspect clear? Okay, there are two unique different cases. The first one is with no independent cases. Okay, now to find out Thevenin's equivalent, it is simple. You just replace all the current sources by open circuit and voltage sources by a short circuit and do. But if there are dependent sources, then again you replace all the independent voltage sources, okay, by a short circuit and independent current sources by open circuit, whereas we will keep the dependent sources as it is in the circuit and externally apply a voltage V0 at the output terminal and try to compute the current, and then RTH we are going to get by using the formula V0 divided by I0. So this will be clear. I will give you an example. We will solve one example. So this aspect will be further clear to you all. Okay. So this is the first simple circuit. There is no dependent source. So this is RL. So we need to find out what is the VTH and RTH. Okay. So this is the circuit to find out VTH, right? VTH. So we have removed the RL resistor. Okay. Can somebody see this diagram and straight away give me an equation to compute V0? Anybody? Voltage division rule we have read, right? Can we apply that here straight away? So instead of trying to find out the current and doing summations and all. Okay. So what we can do is see this is 7. This is 7 volt is already available here, right? So the voltage across here will be 7 plus something here. Okay. What is that something? What is the total potential difference between these 2 points? 28 minus 7, which is 21, right? So if you see 21, how is it going to get distributed between these two elements? That is the 21 into 1 divided by 4 plus 1, right? That is the voltage division rule. So you see these things, and with practice we'll be able to write these equations directly without getting into too many derivations and trying to find out the currents and all. So that will save your time in the exam. See, is it clear how this equation has come? 7 is the voltage which is already available here, so it has to be more than 7 out here. And then the difference in voltage across these two resistances, 28 minus 7, which is 21. And then this is the potential divider rule, right? 1 divided by 4 plus 1. So is this equation clear to all of you? Gautam?
Yes, sir.
Yeah, okay. So this will basically save time. With practice, you should be able to write these kind of equations. So this is VTH. And to find RTH, it's very simple, right? And 4 into 1 divided by 4 plus 1, the 4 by 5, it will come as 0.8. Okay. So this is one example. So this is going to be the final thing which is going to be written, and then you can compute the current going through this 2 ohm. This 2 ohm came from here, okay, RL. So initially we removed this RL from the circuit, and in the final stage, after having computed, we have put back there to compute the current which is through RL. So this is how we do problems based on Thevenin's theorem. Okay, let's take one more example. Now here we have a voltage source as well as an current source. So let's try and find out what will be R equivalent, RTH and VTH. Okay, again here, seeing the circuit, can we say what could be VOC? Anybody? Shreyans? Anybody? It's very simple. Don't try to calculate anything. Just see the circuit. Dheeraj? No idea? See, what is the current flowing into that 2 ohms resistance? Anybody? Siddhant, any idea what is the current going through these 2 ohms? It's minus 1 ampere, right? Yeah, Ganeshwar, the current is minus 1 ampere, right?
Yes, sir. Minus 1 ampere.
Yeah, so what would be the voltage across VOC?
Minus 2 volts.
Yeah, minus 2 volts. So you don't have to, okay, once you see this circuit, don't waste time trying to compute what will be VOC. Straight away is minus 1. We are not bothered about what is happening here on the left hand side of that. Okay, we are only bothered about the what is the terminal voltage available. Okay, here it is very clear. The terminal voltage which is available out here is minus 2 volt. Okay, so straight away we can write, oh sorry, this should be VTH. Okay, I have written RTH, so that correction is required there. Okay, and in this case again, this short circuit, we are going to replace with the open circuit, and this voltage source by a short circuit. So this 6 ohms will get shorted, right? This 5 ohms is also of no use because there is an open circuit here, so that doesn't come into the circuit. So RTH is plain and simple 2 ohms. So see, this was the complex circuit we were talking about actually, and then finally we can just represent it by VTH and RTH, where VTH is minus 2 and RTH is 2 ohms. So you see how powerful this tool is. This complex circuit can be just replaced by these two, and whatever load now we connect, depending on that, it will be simple Ohm's law or a voltage divider rule to find out what will be the terminal voltage. Okay, so it is pretty simple now. Okay, so now let's take one more example of an dependent source. Okay, so that things become clear. Now if you see here, we have a dependent source out here, plus and minus out here. So and this voltage is 2 Vx, whereas Vx is the voltage across 4 ohms. Okay, so in this case we said we have to find out RTH. We have first of all, to find out RTH, we need to remove this 5 amps, which is an independent source, by an open circuit. So open circuit means that is not there anymore. So this becomes that force, and rest of the circuit will remain as such. And then we are going to apply an extra voltage, that is known as a testing voltage. We are going to apply across the output terminal V0. Okay, and we are giving 1 volt. Okay, we are giving it as 1 volt and trying to compute. Okay, you can leave it as a variable also, then all your in the equations you will have one V0 variable, or you can give it as 1 volt and then try to find out and do try V0 by I0. Okay. If you put it as a variable, then again when you do V0 by I0, that variable will get cancelled. But if you put it as 1 volt, and okay, it's better, I guess. It will simplify your equation. So I have put V0 is equal to 1 volt here. Okay. Now after having put V0 is equal to 1 here, this is I1, this is I2, I3. These are the three currents which we have. For the mesh currents, we have denoted as three currents. We have taken all the currents in clockwise direction. Okay, so you can do as per your wish, but here just for the sake of it, I have taken it as clockwise. So for the KPL for loop 1, you have 2 Vx is the source, right? So 2 Vx is equal to actually 2 into I1 minus I2, if you see there, or if you do an algebraic sum across the loop, it will be minus 2Vx plus 2 I1 minus I2 is equal to 0, right? So or from this equation you get Vx is equal to I1 minus I2. So this is one equation which you are going to get out here. All right. Similarly, mesh analysis for loop and 2. So there is one more loop here, and there is one more loop out here, right? And we make the loop equation. So you get two more equations, and also we have minus 4 Ix is equal to Vx. Okay, so because this Vx we are getting it across 4 ohms, and the current which is flowing there is I2 from the negative to positive. That is why you have an minus sign here. So minus 4 I2 is Vx. So you got one more equation out here, and making the loop mesh equations for loop 2 and loop 3, you get two more equations. Now we solve all these equations and we find out the value. We get the value of I3. I3 is minus IO. Again, you see these things we got to be careful, because I3 we have taken it as an clockwise current, whereas we are interested in finding out what is the current being pumped into the circuit by the voltage which source which we have put here. So we are interested in finding out what is IO. So that will be minus I3. So once we get a value of I3, I0 is minus I3, so 1 by 6. So V0 we have taken it as 1 volt. So 1 divided by 1 by 6 I0. So you get 6 ohms. So that is how we compute RTH whenever there is a dependent source. Okay, essentially only the independent sources are removed. Dependent source we leave it as such, and then we put an external voltage source. Okay, sometimes even the dependent source will become 0. Okay, I can give you an example. Suppose this voltage source this 5 ohms is in series with this 4 ohms, right? So in that case, what happens? We are going to remove this 5 amps, right? So this 4 ohms will become open circuit, and if it is open circuit, there will be no Vx, and if there is no Vx, this will become 0, right? So in such cases, you can do that also, right? So this will become 0, so you can put a short circuit there. So those things also you have to be careful. Okay. Okay, we found out VTH. Now we need to also find the no load or open circuit voltage to find out VTH. Again, in that case, we are going to consider this 5 ohms also. Okay, so not that for V open circuit, remember these have to be considered. Okay, it is not that we remove this dependent sources in both the cases. Only to compute the resistance, equivalent resistance, we remove these sources, but whereas to find out the open circuit voltage, we have to keep this resistance. Okay, so this is going to be. So again, there are 3 meshes. So you write in the first mesh you have I1 is equal to 5, and then you write right here you have I2, I3. So you write all the 3 equations for each of these things, and then you will get 3 equations of these 3 variables. and then compute and then try to compute the value of I1, I2, I3. Once that is done, the output circuit voltage will be, see, we have left this open out here, so there won't be any voltage when across 2 ohms. So you can assume, so the voltage which is available across A, B is the voltage which is available across 6 ohm. Okay, you have to be careful with these things. There is no current flowing across 2 ohms. Okay, so what is the voltage drop? You can assume no current means I is equal to 0. So 0 into 2 ohm. So this potential drop across 2 ohm is 0. So you have to in fact find out what is the current across 6 ohm. So once you solve the equations, you will get the value of I2. So I2 into 6, whatever is the voltage, that will become OC, and that is our VTH. Okay, so that once you do that, I'll share this PDF. You try to solve these equations all by yourself once. Okay, these problems which are there, and also the tutorials. That will be good enough for your exams. Okay, so and then try to see whether you are getting these results. Okay, if you are getting these results, then I think you have understood the concept, and you don't have to put anything extra for your exams. Okay, is it okay, this problem, how to handle these kind of problems? And then you connect a load resistance if the problem says further ahead, okay, what is the current in the load resistance, then you simplify this, and then you put the load resistance there, and you can use the voltage division rule to find out. If I connect another 6 ohm load, then the voltage across that will be say 10 volt, or if you are connecting anything greater than 6 ohm, it will be more than 10 volt, depending on the ratio of RL and this, right? So that equation we know, voltage division rule. Okay, so that's all. So before we wind up today's class, you got to remember that Thevenin's theorem, okay, is applicable only where all the elements are linear. So this is the limitation, that we cannot have an apply Thevenin's theorem into a circuit which has got non-linear elements. Okay, so that's all for today. In case you have any doubts, you can ask me now. Anybody? No? Okay, then thank you.